Hi class, we are now on chapter 6.8. We're going to look at empirical formulas and start doing some calculations. Excuse me. So empirical versus molecular. I like to call empirical formula the skeleton. We all have skeletons, but the molecular formula is the outer layer. That is what makes us look different from each other. So we can all share the empirical. We all have the same skeleton, but the molecular is what makes myself look different from you and so forth. That's that outer layer. So if we look at this, the empirical formula is the simplest ratio of elements, and it cannot be reduced down any further. So if we look at this empirical formula, we cannot reduce this down any further because then we'll get fractions, and we don't want fractions. The molecular, we can get the molecular from this by multiplying this. So if you see, we have a 6, 12, and 6. So if we multiply these by 6, we get 6 here, but we use them as subscripts, not as coefficients. We get 6 times 2 is 12, and 6. So this is, again, what I call the skeleton and the outer layer, which is the molecular formula. So by using the empirical and using a multiplier, we can determine what the molecular formula is and vice versa. So here's a list of empirical formulas. Here's a list of empirical formulas, and you can see water and carbon dioxide, the empirical and the molecular are the same thing, and that happens. You may be dealing with a compound that actually is both. So water cannot be reduced down any further, and it's in its simplest state. But as you can see, as we go down, we start seeing that even though these, you cannot reduce these down anymore because you would get a fraction with oxygen. But then you can see what you need to multiply to get these actual compounds. These are the actual compounds that we know. These may not always be. These might be just the skeleton form of it. And a lot of compounds share the same skeleton form, an empirical formula. So the lowest whole number ratio of atoms in a compound. So if we look at acetic acid, and I said I want the empirical formula, well, you can tell with this, we can reduce it down. So we can reduce it down by 2 and not by 4 because then we get fractions. But reducing it by 2, we end up with the empirical formula that I just showed you on the other page. So if I give you a molecular formula of benzene and I tell you to reduce it down, it's very easy. You can see what you need to reduce it down to, and here is the empirical formula. And again, there's a lot of compounds that have just CH, a lot. It's the skeleton, but when you use a multiplier, which is what we need to multiply to get this, then we get a specific compound that's specific to benzene, which is 6 carbons and 6 hydrogens. So here, let's take a look at, so empirical formula gives the smallest whole number ratio of each type of atom in the compound, but it doesn't give you the molecular. It just gives you the skeleton. If you want to know exactly how many atoms are in a compound, you need to look at the molecular. That's going to tell you. So for instance, if we look at hydrogen peroxide is H2O2, but the empirical formula is HO. How do we get from this to this? Is with a multiplier, this n. We need to determine what it is to, what do we need to multiply this to by in order to get this. And again, when we multiply this, we multiply them in subscripts. We don't do coefficients. So we can easily tell that n equals 2. So I would multiply 2 here and 2 here, and that gives us this. But we can also use mass percent. Mass percent is going to come in a little later. So if we were given an experiment and it produces 3 grams of hydrogen and 24 grams of oxygen, we want to know what the empirical formula is. We only have the masses of what's produced, but that's not going to give us a chance to determine a chemical formula, more or less even a molecular formula. So we need to get the empirical to start with. So the steps never change. That's the good thing, is no matter how difficult a problem is, the steps for empirical don't change. If you have grams, we need to get them out of grams. We need moles because the only thing we ever work in is moles. So we have 3 grams of moles. We convert 3 grams of hydrogen, convert it to moles. And then we have 24 grams of oxygen, convert it to moles. So we end up with 3 moles of hydrogen for every 1.5 mole of oxygen from this mass of these hydrogen and oxygen. But we're not done. We need to figure out the empirical. Again, the steps never change. So in this case, make a pseudo formula for water, because we believe we have water, but we need to make sure that that's what we have. So make a pseudo formula with the amounts that you calculated, and then you reduce by the smallest value. In this case, it's 1.5. So we reduce by the smallest value, and that ends up giving us H2O. So these steps are not difficult, but the problems may look overwhelming. But the thing is, the steps never change. If you have grams, get to moles. Once you get to moles, divide by the smallest value, and it will give you your empirical. There are some problems sometimes, but we'll cover those. Write down. So here's the steps. If you have the masses, then you get from grams to moles. What if you're given a mass percent? If you're given a mass percent, we've already covered mass percent. Get it out of percent and make that out of 100 grams, because a percent is out of 100. So in this case, it's 100 grams, and whatever that percent was, for instance, like 39%, now it's out of 100 grams. You now have 39 grams of sodium. Convert the masses to moles with molar mass. Write down the pseudo formula, and then write them as subscripts. Divide all by the smallest subscript, so the whole compound has to be divided. If the subscripts are not whole numbers, so if you get whole numbers, great, you're done. But if they're not whole numbers, then you have to start multiplying all of the subscripts until you get whole numbers. So if you get a compound, this is actually showing you, if you get a compound with this, what to multiply it by to get a whole number. So for instance, if I end up with a hydrogen with a 0.66, I can multiply it by 3 and end up with 0.99. That gives me 1. If I have 0.75, I can multiply it by 4. It also gives me 1. So this is a chart that you might want to refer back to if you start getting values that don't have whole numbers. All right, so let's take a look at a problem. A 3.24 grams of titanium reacts with oxygen to form 5.40 grams of metal oxide. What is the empirical formula of the metal oxide? Now, there's a few things here. We are given the metal, the sample. This is very familiar. This is very similar to the mass percent that we covered. And we're given the whole. So we have a part and a whole, but we're not doing percents now. But there is something you can do, because we don't know what the metal oxide is. Titanium has, look at, I fixed one of these. Okay, this is all messed up. I fixed some of the other slides. I didn't fix this one. It just repeated itself. So break this up right here. We have titanium, but we have oxygen. But we don't know how many oxygens, and we don't know the oxidation state of titanium. So in this case, we need to figure, and we're not going to be able to get that. That's what we're trying to figure out, what the empirical formula is. So how do we get the amount of oxygen? Well, we can subtract. We can subtract the whole, the part from the whole, and that will give us the amount of oxygen. Still doesn't tell us how many, but we know now how many oxygens we have due to the law of mass of conservation. So this is what this pretty much says. We can't convert the mass of metal oxide into moles because we don't know the chemical formula. That's what we're trying to solve for. But we're given the mass of titanium, and we're given the mass of the whole compound. So we can subtract the titanium from the compound, and the difference is actually oxygen, because that has to all go back to the law of conservation. We don't lose any mass. It all has to be accounted for. So that's what we do. We take the mass, which is 5.40, and that's a combination of both of these. We subtract the Ti, and it gives us 2.16 grams of oxygen. Now this is going to be very similar to the other problem that we did. We get it to moles. Then we do our pseudo formula, and then we reduce down by the smallest value. And the formula for this is Ti2O. So once you get these down, it's very nice. This worked out easily. All right, so let's do another one. A 1.56 gram sample of copper reacts with oxygen to form 1.95 grams of a metal oxide. So again, we have copper and we have the metal oxide. What is the formula of the metal oxide? So we know when you see metal oxide, oxide is oxygen. So the metal is the metal that they're talking about. So in this case, it's copper oxide, but we don't know the oxidation state. That's what we're trying to figure out. So we have 1.56, and the whole sample is 1.95. So in this case, we are going to look, we're going to do some subtraction. And in this case, we do the 1.95, which is the whole compound, and we subtract 1.56 copper. This gives us 0.39 grams of oxygen. Now we're going to do the same thing we've been doing. You get to the moles, and you get to the moles. Sorry, this moved over. And these also moved over. I am sorry. I checked these, and then I don't know what happens to them when I hit to record. So we end up with moles of this, and we end up with moles of this. So now we do our pseudo formula, and this is divided by this is divided by this. We still end up with 1. So we have copper oxide, which is actually copper 2 oxide. They've just been reduced down. And that's it.